Okay, so let's go through and just, we'll go question by question. I may not work everything out in its entirety, but I do want to make sure we're talking about how much work you need to be showing on these problems in order to get your credit. You know, it's not so much that I have to see every little step, but if you make a mistake and I don't know where your mistake is, then I can't give you partial credit. So if you want to have the chance for partial credit, you have to make sure that you're showing me everything along the way. All right, so let's look at the first one. If we look at this one, it asks us to find the mean. And I do apologize. I wasn't clear on this question whether your set was a sample or an entire population. That doesn't impact anything in your calculations except your standard deviation and variance. So I apologize for that. On the test, I will make sure it is clear. Like number 2, I did tell you it was a sample of mutual funds. On number 1, I should have either said, you know, a portion of the class, or this was everybody in the class, so you would know which one it was. So we might have slightly different answers depending on how you interpreted that one. But the mean is the same either way. You just add them all up and divide by the total number. So if you add all those up, you get 560 divided by 10, since you're showing me the work, and that's 56. So just because we had some, like on the quiz, that you just added things up wrong, just show me that step so I know. The median. If you want to find the median, you have to put your numbers in order from small to large. Okay, there's 10 values. So the median is the middle, which would be between the 5th and 6th values. So since there's 2, we have to add it up, divide by 2, and you get 57. Mode. This is the only thing you could have more than one of. You know, we only have one mean, we have one median. It is possible to have multiple modes. My 58 shows up 3 times, so that is the mode here. If I had another number that also showed up 3 times, you would list both of them. D, the range. So show me your work. When I find range, what do I do? So my highest is 61, minus 51 is 10. E, 5-number summary. If you guys forget anything, remember, you have this formula sheet and everything is on here. If you look, the very last thing under chapter 3 was the 5-number summary. So it tells you it's the minimum. So my minimum value is 51. Comma, quartile 1. So we have to look. Quartile 1 is essentially just the median of the lower half of the set. Okay, we know the mean, or the median was right here. So if I found the median of this group, that would be 53. Quartile 2 is the same as our median, which we already said was 57. Quartile 3 is the median of the higher group. So that's 58. And then my highest value is 61. So 5-number summary there. F, interquartile range. Again, if you forget anything, it's on your formula sheet. I'm pretty sure it's on there. Yeah. IQR, interquartile range, quartile 3 minus quartile 1. So quartile 3 was 58 minus 53 equals 5. Okay, G, box and whisker display. The only problem that I've seen with these is you're not spacing things out correctly. I don't want you to just go down here and mark like your 5 numbers randomly from your 5-number summary. I want an actual scale with those numbers spaced out where they need to be. So I'm going to count by 2s. Your whisker goes down to the lowest value as long as it's not an outlier. I didn't even have you calculate for outliers here. We didn't have any. If you have an outlier, what do you put there? Just an asterisk. And then your whisker goes down to the lowest value that is not that outlier. So like if I had a 40 here, I would just put a star down at my 40 and then I would start at my next highest value, or next higher value. So we're at 51 for the start of my whisker. The box begins with your quartiles. So 53, it should end at the 58. Mark your 57. And then this whole thing should end at 61. Okay. H was standard deviation. I am not going to work this out entirely, but I just kind of want to run through. If you're looking at standard deviation, and this is where you might have had a difference whether you treated it as a population or a sample, so I apologize for that. If we treat it as a sample, I gave you a table, but you kind of have to know what to put in the table. So the first column was just for my x's. Then if we look at this, the next thing we're going to do is for each x, we're going to subtract the mean. So we have to have a space for that. And then I have to take that number and square it. So those are my 3 columns. So you list all your x's, subtract your mean for each, and square it. Are we okay with that? On the quizzes, sometimes you guys stopped here, but have you answered the question? No, I wanted the standard deviation. So I want my S or sigma, depending on whether it's a population or a sample. If you treated this as a sample, the formula says, what does this symbol mean? Sum. So we add up this final column. So if I add all those up, I get 100 divided by, what's n? Number of points. So this was 10, so 10 minus 1 is 9, and if you do that, you get 3.3333. If you had treated this one as a population, the difference in the formula is you just divide by plain n. So if you look on the formula sheet, it tells you that. And then you would have gotten 3.1623. So for this problem, either one would be okay because I wasn't clear. Okay. How do we find variance? S squared. So if I just square that number, we get 11.1111. If you were treating it as a population, your sigma squared should turn out to be 10. Maybe slightly different if you use this rounded number, so close to 10 anyway. All right. Questions on any of those? Let's talk about the shape of our data. So a couple ways to do that. We can look at, some of you like to make histograms on your calculator and look at those. We can also look at the box and whisker display. So this, my mean was what in this problem? 56. So was there a big difference between my mean and my median? No. In general, if the mean and the median are close to the same, it's pretty well symmetric. Now, a lot of times we can tell if one tail extends really far, that tells us it's skewed. We can also look at, we've talked about how the mean and median are related, you know, if they're the same, it's symmetric. If the mean is smaller, that meant there were more small values that drug it down, so that would be skewed to the left, right, if you have more small values. If the mean is higher than the median, there were more high values that brought your mean up, so that would be skewed to the right. This one I would accept, if you said symmetric or bell-shaped, I would take that here. It is fairly symmetric. You could have also told me slightly skewed left because my mean is below my median, so I had some low values that drug it down. You can also tell if you mark the mean in your box, you can see that you do have a longer extension out to the left. So, a couple different ways. This one is not obviously one or the other. It's fairly symmetric, but with a slight skew. Any questions on number 1? So number 2, we have a sample of mutual funds. So this one you are just strictly putting in your calculator. I am not going to take the time to do that unless I need to, so I'm going to write down what you should have gotten. But you just go to your L1, you enter all those values. Standard deviation. It told us that this was a sample, so for your standard deviation you should be looking at that S sub x. And you should have gotten 0.0960. Quartiles are given on your calculator along when you go into those one variable statistics. So quartile 1 should be negative 0.005. Quartile 2, 0.02. Quartile 3, 0.085. IQR, I don't think that one's given on your calculator. How do we find it?
Q3 minus Q.
So Q3 minus negative 0.005, and you should get 0.09. Questions there? See the interpretation. A quartile tells you what percent is below, at or below that number. So quartile 3 means 75% of the data is the 0.085 or below. Part D, upper and lower fence. Again, anything you don't remember is on your formula sheet. If you look at that chapter 3, it tells you one of the last things there, your formulas for both of them. So lower fence is quartile 1 minus 1.5 times the IQR. So my quartile 1 was negative 0.005 minus 1.5 times my 0.09. This is why it's so important to show me work, because if you got the wrong answer on your IQR, you're going to miss your upper and lower fence. But as long as I have the work to know why you're getting the answers you're getting, I only count off that first time. So if we do that, we get negative 0.14. Upper fence is quartile 3 plus 1.5 times the IQR. So quartile 3 is 0.085 plus 1.5 times 0.09, and that gives us 0.22. So that's your window. Anything between those numbers is okay. Anything smaller than negative 0.14 or bigger than 0.22 is an outlier. So looking at your data, do we have any outliers? Yes, what? Yep. 0.29 is an outlier there. Okay. So far, so good? Is this helping you guys at all? Number 3, we had a ton of questions on this one, so let's talk about it. The mean serve speed of a tennis player was 101 miles per hour, and the standard deviation was 14 miles per hour. If the distribution is bell-shaped, what percentage of the data will fall between 87 and 115? So this is talking about what percent falls within so many standard deviations of the mean. And we have two rules for this. We have an empirical rule and we have Chebyshev theorem. When do you use each one? If it's bell-shaped, we can do empirical. And that one is on the formula sheet and it is spelled out completely. It says empirical rule, if the shape is bell-shaped, and then it tells you. The other one is the only formula that we have that is not on our formula sheet. So that is the one and only formula I'm asking that you memorize. We wrote it on our formula sheets when we talked about it, but you will use a copy of my formula sheet when you take the test so that there's nothing written on it. So you do need to know Chebyshev's, and that's the 1 minus 1 over k squared. So empirical rule works if it's bell-shaped. Chebyshev's always works. So if we look at this, part A does tell us that it's bell-shaped. So we need to figure out how many standard deviations we are from the mean. I think the easiest thing that we've done is just kind of found the standard deviations. We know our mean was a 101, and it told us the standard deviation was 14. So if you're talking about the first standard deviation, you have to do the mean minus your standard deviation. So 101 minus 14 is 87. 101 plus 14 would be 115. So if you're between 87 and 115, that's the first standard deviation. If I wanted the second standard deviation, what would we do? 87 minus 14, 73. 115 plus 14 is 129. If I wanted the third standard deviation, what do you do? Same thing, just keep adding and subtracting. So 73 minus 14 is 59. 129 plus 14 is 143. And we could keep going with this if we needed to. Part A says between 87 and 115. So that tells me it's one standard deviation. It's bell-shaped, so that says empirical rule. So you look at your formula sheet. What does the empirical rule say for one standard deviation? 68%. Part B. This time it says between 59 and 143. So what's that? The third standard deviation. It says nothing is known about the shape. So I can't use the empirical rule because it's not bell-shaped, so we have to use Chebyshev's. Our K is our number of standard deviations. So K is 3. So 1 minus 1 over 3 squared. And you get 0.8889. So that would be 88.89%. Questions there? Number 4. A student receives test scores of 62, 83, and 91. The term project score is 88 and her homework score is 76. If each test is worth 20% of the final grade, the term project is 25%, and the homework is 15% of the final grade, what's the score in the class? So this is like a weighted average problem. We've done some before. They were a little bit different. Like I think we did a coffee one maybe or something. I don't remember really. But you had to take like the number of pounds times the price per pound and for all of them, and then divide by the total pounds that we purchased. This is talking about our grade, so we are going to take the score times the weight of the score. So 62 was a test. It said every test is worth 20%, so I'm going to take it times 20. And the next test, you got an 83, and that's worth 20. And then we got a 91, and that's worth 20. The term project was 88, and how much is the term project worth? 25. And then the homework, we got a 76, and homework was worth 15. When I divide this, we could just know percents are always out of 100, so divide by 100, or if you add up all those things, we get 100. So that's what I'm dividing by. And you should get 80.6%. Again, show me work on your test. Don't just write down an answer. Show me where it came from. Questions there? Number 5. So a student scores 62 on the geography test and 261 on the math test. The geography test has a mean of 80 and standard deviation of 115. Math test has a mean of 300 and standard deviation of 26. On which test does the student score better? So it's not obvious just looking at this. I didn't give you percents. I just gave you a score. So we have to find a way to compare them. How do we compare different sets of data? What do we have to do? Z-score. We have to translate them into a common unit. So we're going to find the Z-score for each. So we have to do the geography and the math. Again, all you have to do for this is look at your formula sheet, and it's all right there. So the geography test, to find our Z, you do X, that's your score, so your score on the geography was a 62. Come in. Minus your mean. Oh, okay. Your mean on the geography test was an 80. Divided by standard deviation on the geography test was a 15. So if you calculate that, you get negative 1.2. Okay, the math test, your score was 261. Average on the math was a 300. Standard deviation on the math was a 26. We should get a Z of negative 1.5. Why are those things negative? What's that tell me? Right. The negative just means it's below average. So if you think about this, here's your average, your mean. Negative 1.2 means you're 1.2 standard deviations below that. So here's geography. Math was negative 1.5, so you're even further down. So which one was better? Geography. If those numbers had been positive, which one would have been better? The furthest away from the mean, so it would have been your math one, because you would have done better than average. Questions there? Numbers 6 and 7. Those kind of are asking the same thing. We've talked about when we did measures of central tendency and dispersion, which things are resistant and which are not. Resistant means that outliers don't really change them. And if it's not resistant, then having one extreme score, one really high or really low, has a huge impact on it. So, a lot of you weren't sure on this. Let's make sure we understand. When I'm trying to decide mean, median, mode, I make my decision based on the shape of the data. We have one option if it's symmetric and one option if it's skewed, and we have outliers. Ideally, mean, median, mode, which one tells you the most about the data? Probably the mean, the average, right? But if we think about that, if you guys take your test tomorrow and Karina's absent and I give her a 0, what happens to the average on the test? It goes way down. The mean is not resistant at all. Having one value off really has a huge impact on it. So, in that situation, what would be better? The mean, median, or mode? Median. Does the mode really give us much information at all? No. So it's kind of not something we would ever choose. Okay, central tendency. We have the same thing. We talk about symmetric and skewed. Okay, standard deviation. We make that big table. It gives us a lot of information. It tells us how spread out our data is. So as long as our data is nice and symmetric, that's what we want. But what happens if you throw one really big value in there? What happens to that table if you throw in a big number? Does it change it a lot? Yeah, one strange number has a huge impact on it. So standard deviation is not resistant. In that case, if it's skewed, we want the interquartile range. That basically gives you a window for the middle 50% of your data. So that would be better if you had outliers. Number 8. This one was a calculator problem. So you have to enter your data in your L1 and your L2. I don't really want to take the time to enter all that, but you guys know how, right? And then if you have data in both of those, what do you have to do? What kind of statistics? 2 variable statistics there. Okay, so if I run my 2 variable statistics, it's going to give you x's and y's. So x bar.
That's because to sign.
Sure. So your x bar comes out to be 223.47. Your standard deviation of x, 21.797. We do the same thing for the second car. Did you guys get those numbers? Know how to get them? So go to your 2 variable stats and you just scroll through the list until you get the pieces. We're trying to compare these. So we want to know which car would be a better investment. The mean is telling us we were looking at how far it travels on 10 gallons of gas. So the first one can make it 223 miles, the second one makes it 229. Is there a huge difference there? No. 10 gallons of gas, the second one gets you 6 more miles. Not a huge difference. So it doesn't make it really obvious that one car is superior at that point. If you look at your standard deviation, what does standard deviation tell us? How consistent it is. The smaller your standard deviation, the less spread out it is, the more consistent. As your standard deviation grows, that means there's more variability in your data. If I'm looking at those, car 2 has a much larger standard deviation. That means it is much less consistent. Sometimes you get really good mileage, sometimes you get really bad mileage. So if I'm looking at that, which car would be better? car 1. Because in just terms of their average, there wasn't a big difference, but car 1 is going to do the same thing more consistently. So it would be a better option for us. Number 9 was a scatter plot problem. So you guys know you enter that in L1 and L2 and you get your scatter plot. Everybody knows how to do that? What kind of relationship did you see there? Negative linear relationship. Linear correlation coefficient. If you forget what that means, look on your sheet. It tells you correlation coefficient R equals. So it tells you you're looking for R. Your calculator gives you that. You have to have your diagnostics turned on. So if yours are not on tomorrow when you go to take your test, you make sure you go into your catalog and turn that on so you can get your R. And you should have gotten R to equal negative 0.9805. D. I asked if a linear relationship existed. A lot of you missed this on the quiz because you didn't give me anything to support your answer. You know, just looking at this negative 0.98, that seems like a pretty strong relationship. The negative just tells me it's a decreasing line. But if I want to back it up, I have to use that table too. So look on your formula sheet. Table 2 is the back of the second page. You have to have an n. What's my n on this one? Number of values. So we had 7 points, so my n is 7. The critical value then for an n of 7 is 0.754. So at the very least, if you're justifying this, I want you to write down your critical value so I know that you were looking at the right thing in the table.
How did you get that?
I read it from the table.
Okay, got it.
So you go to the n equals 7 row and then just copy down. Now, I want to decide if that's enough to be linear. So the rule was if the absolute value of R is bigger than your critical value, it's significant. Okay, because the negative just told me the line was decreasing. So this is bigger than 0.754. So yes, that's a linear relationship. Is that okay? Part E. Find and interpret the coefficient of determination. So if you don't remember what coefficient of determination is, look on your sheet and it tells you. And it even really tells you how to interpret it. The coefficient of determination, R squared. So you can look at your calculator and just copy down. When it gives you R, it also tells you R squared is 0.9614. And then on a formula sheet it says that measures the proportion of the total variation. So that's like saying 96.14% of the variation let's see. And the response variable, that's our Y. So in Y, or the well-being index, is explained by the regression line. So far, so good? F, the actual regression line, that's just off your calculator. When you run that regression, it tells you y equals ax plus b, and it gives you a and b. We do use y hat for our regression line. So negative 0.0479x plus 69.0296 is what you should have got. G, interpreting the slope and y-intercept. So your slope. When you find slope, you do y over x. So we could think of this as being over 1. Looking back at my original data, y was my well-being index. So this is like saying the well-being index it was negative, so that means it drops by 0.0479 over 1. My x was my commute time in minutes for every minute of commute. So if you add 1 more minute to your commute, your well-being index will go down by that much. Your y-intercept, that's like when x is 0. So saying if there is no commute, the well-being index is 69.0296. H asks us to predict the well-being index of a 25-minute commute time. So what do? Yep, that's like saying your x is 25. So if you plug that in, you should get 67.8. Residual. If you don't remember the residual, it tells you on your formula sheet. Residual is observed minus predicted. Observed is the actual point we saw. So when you look at your original data, when commute time was 25, we saw a well-being index of 67.5. Minus predicted is what you got from your line. So my predicted was what we just calculated, 67.8. My residual is a negative 0.3. J, graph your residual plot. You guys all know how to get to that on your calculator. Go to your stat plot, and I'll have to look at your calculator, or you might have to use the one on your Chromebook for that if you can figure it out. You have to go to your stat plot, and you change your Y2 to residual. You guys know how to get that. You go into second stat. It gives you your list options, and you should have residual there. So when you graphed it, it looks something like this. Remember, it's linear if that's essentially falls between two horizontal lines. If you see a pattern or it makes like a cone shape, then it's not a good model. So does this one have any obvious patterns? No, so it's a good linear model. Okay, number 10. First thing I asked you to find some information on the calculator, so you enter your data into L1 and L2, run your 2 variable statistics. You should get these values. Okay, part B is the correlation coefficient by hand. I think I gave you one more column than I did when I did it in class. I just made one where you could put your ordered pairs, if that helped you. If you look at your formula sheet, first thing under chapter 4 is the correlation coefficient, and it kind of tells you the things that you need. You need to find each x minus the mean divided by the standard deviation. Same thing for the y's. And then what do you have to do with those two numbers? Multiply them. I'm just going to put the product. I don't want to write all that out when I multiply them. So can you guys fill in this table? You know how to get that? Now, does just making the table answer the question? No. Now we have to do the formula. So R equals. When you see that funny looking E symbol, what's that telling me to do? add them up. You're adding up everything from that column. And when you do that, you should have gotten 3.9778. Now, this is why your work is so important, because if you round just one number differently, then it will change that number. So I have to know where everything's coming from. Then we divide by n minus 1. So we had 5 points. If we subtract 1 from that, that would be 4. And we should get 0.99445. 0.9945. Part C, once you do the regression by hand. So look on your formula packet. It tells you, and if I say by hand, that means you better show me the work. Otherwise, I'm going to assume you just wrote it down off your calculator. So it tells you to find b sub 1, you have to do r times the standard deviation in y over the standard deviation in x. So we have our r, standard deviation in y, divided by standard deviation in x. And if we calculate that, we get 2.0233. So that's your slope. Your b sub 0, if you look on the formula sheet, it tells you that's y bar minus b sub 1 times x bar. So the y bar was an 8.6. B sub 1, x bar was 5.4, and that gives you a negative 2.3258. So we get that. So if I say by hand, you better have the work to show me that you did it by hand. Number 11. The linear correlation between violent crime rate and percentage of the population with a cell phone is negative 0.918 for the years since 1995. Does that mean that increasing the percentage of the population with a phone will decrease the violent crimes? So negative 0.918, that's a pretty strong relationship, isn't it? So does that mean if I give more people phones, the crime rates will go down? Why not, if it's such a strong relationship? Okay. Just because they're related, does that mean one causes the other? No. There's some kind of relationship there, but there's no proof. Correlation doesn't mean causation. Just because there's a relationship doesn't mean one causes the other. There could be some third variable that is impacting both of them. What did we call those? Do you guys remember? Lurking variable. There might be a lurking variable out there that's impacting both of them. So we can't make the assumption that one would change the other. Number 12, we're trying to look at these residual plots and decide if a linear model would be good. So, is the first one good? Yes. What about B? It's not, because it has a pattern. It's kind of that U shape. If there's a pattern, it's not a good model. What about C? No. Why? Yeah, it's got that V shape. What did we call that? Do you guys remember? Constant error variance. What it's saying is it's really good at the beginning, but as time goes on, it's no longer a good model. It becomes more spread out. So that's constant error variance. Is D a good one? No, it's got a pattern too, doesn't it? And what else does that one have? It has an outlier in it as well. We see that one point that doesn't fit in with the rest. Okay, last question. Number 13. If you went back to problem 9 and took out that point. So in problem 9, we've already wrote that regression line. So if you go put your data in without the point and you get a new regression line, how do you tell if it's significant or not? Yeah, we graph them. You've got your scatter plot, you go to your y equals and enter those two equations in your y1 and your y2, and we're looking to see, are they different? When you graphed both of those lines, was there very much difference? No, they were practically on top of each other. So was this an influential point? No. If it's influential, then it will change the line significantly. Okay, do you guys have any questions for me?
Do you have blank ones in here?
You can check if there's any extra ones. If there aren't, I can run some more off and have them after.